Ever feel like your phone is full, like before you even download anything new?
Yeah,
It's like you hit some invisible wall, like
definitely.
the limits of data storage, they're holding you back.
I feel that.
Well, get ready because today we're diving into the future. We're talking about a wild breakthrough. It could mean storing all your data, maybe even like your entire digital life on something, like the size of your fingernail.
Wow, that future, it might be closer than we think, thanks to some seriously strange physics.
We're talking about antiskyrmions.
Okay.
Honestly, the first time I read this research, my mind was blown. Picture this: tiny, swirling magnetic fields.
Okay.
Like imagine microscopic tornadoes, but they're stable, holding their shape. Those are antiskyrmions.
And these aren't just some theoretical, curiosities. They have the potential to completely change how we store information, making hard drives exponentially faster, denser than anything we have today.
But here's the catch. Studying these things, even with crazy powerful computers, it's unbelievably complex.
Right.
It's like imagine trying to simulate like the weather patterns of a hurricane.
Oh, wow.
But on the scale of atoms, it's a computational nightmare.
Yeah. That's where the AI comes in.
Okay.
The research we're looking at today uses AI, specifically convolutional neural networks, to predict how these magnetic systems behave with ridiculous accuracy.
Okay, so before we get too far ahead of ourselves here,
Yeah.
we've said antiskyrmions a bunch of times now. You
Mhm.
said, like, swirling magnetic tornadoes, but where are these things actually found? What are we talking about here?
So they arise in a very specific type of magnet called a chiral magnet.
Okay.
So picture this, right? Instead of your average refrigerator magnet, like the one you have on your fridge, imagine one with a built-in twist,
Okay.
like a spiral staircase.
Got it.
That handedness, that inherent twist, it's crucial to how these materials even behave.
So not our parents' magnets, that's for sure. But why is this twist so important? I mean, what makes a chiral magnet different?
It all comes down to something called Dzyaloshinskii-Moriya interactions.
Catchy.
Yeah, I know the name itself is a mouthful, but just know these interactions are what give chiral magnets their unique properties,
Yeah.
making those swirling magnetic textures possible in the first place.
Okay. Dzyaloshinskii-Moriya. We'll take your word for it on that one. But let's get back to the stars of the show here, the antiskyrmions. You mentioned that they're like the mirror image of something called skyrmions.
Exactly. It's subtle, but that anti-prefix, it makes a world of difference.
Okay.
While they might seem similar at first glance, antiskyrmions are like the mirror image of skyrmions. Think of it this way. If a skyrmion is a swirling vortex, an antiskyrmion is a swirling vortex spinning in the opposite direction.
So it's all about which way they swirl.
Yeah,
Why does that matter?
that difference in swirling, which physicists call helicity, it has insane implications for how these magnetic structures behave. The specific type of antiskyrmion in this research has a helicity of 0, meaning their twist is neutralized in a way that makes them perfect for things like data storage. Imagine them as tiny controllable magnetic switches that could be flipped on and off to represent the ones and zeros of digital information.
Zero helicity. That sounds like the magic ingredient here. But from what you've said about simulating these things, I imagine it takes a long time to even figure out how these antiskyrmions will behave.
Right. Yeah, you're absolutely right. Traditionally, studying these magnetic systems involves running crazy complex simulations, which, as you can imagine, takes a lot of computing power and even more time.
So how did these researchers manage to kind of crack the code, so to speak? You mentioned AI and convolutional neural networks earlier. Those are those things that can recognize cats in pictures, right? But how do you teach a computer to predict the future of a tiny magnetic tornado?
That's the beauty of this research. It's all about recognizing patterns, just like a CNN can learn to identify the shape of a cat's ear in an image. It can also learn to recognize patterns in the way these magnetic spins evolve over time.
So instead of feeding the AI thousands of pictures of cats, they fed it what simulations of these magnetic swirls?
Precisely. Think of it like this. Imagine showing the CNN a flip book with each page representing a snapshot of the magnetic simulation at a different point in time. By analyzing those snapshots, the CNN can learn to predict what the next page of the flip book will look like, essentially forecasting the future of the magnetic system.
Wait a minute. So they're saying this AI can look at a few frames of this magnetic flip book and tell you what the final picture will be.
That's exactly what they found. And here's the truly mind-blowing part. The CNN doesn't even need to see the entire simulation to make accurate predictions in this research. They found that using data from just the 6th snapshot out of 20, was enough to predict the final magnetic structure with a remarkable degree of accuracy.
Let that sink in for a moment. They can tell where these magnetic swirls will end up just by looking at the very beginning of the simulation. That's incredible, but how accurate are we talking? Can it predict everything perfectly?
It's not perfect, but it's remarkably close. The accuracy does vary depending on what specific feature you're looking at. For example, identifying the presence or absence of those antiskyrmions. The CNN nailed it almost every time, even from those early snapshots. Predicting how those antiskyrmions would arrange themselves in a larger pattern was a bit trickier, but the results were still far beyond what anyone expected.
This is all starting to sound like a physicist's dream come true. But how do they actually visualize and interpret all this data? I imagine it's not just staring at a screen full of numbers.
You're right, visualizing the result is key. That's where phase diagrams come in.
Okay, phase diagrams. Those always sounded intimidating back to my science classes.
They don't have to be, think of a phase diagram like a map. Just like a map uses coordinates to tell you where things are located. A phase diagram uses things like temperature and magnetic field strength to show you what kind of magnetic structures you'd expect to find in a material under those specific conditions.
So it's like a cheat sheet for understanding how these materials behave under different circumstances. I like it, but how do the CNNs fit into this picture?
Traditionally, creating these phase diagrams involves running countless simulations across a vast range of parameters. It's a painstakingly slow process. But what these researchers discovered is that the CNNs could be used to create these phase diagrams much, much faster.
So instead of running a full simulation for every single point on that map, the CNN can take a quick glance and say, yep, looks like we're headed for anti-skyrmion territory over here.
You got it. And here's where it gets really interesting. The CNNs were able to pick up on some subtle but potentially very important details that might have been missed using traditional methods.
Like what? Give me an example.
Well, in a certain region of the phase diagram, the CNNs consistently identified the presence of something called an antiskyrmion gas.
An anti-skyrmion gas? Okay, now you're just messing with me. What in the world is that? An anti-skyrmion gas. Okay, now you're just messing with me. What in the world is that?
It's not as outlandish as it sounds. Imagine a crowded room where everyone's moving around randomly, bumping into each other.
Okay.
That's kind of what's happening in an antiskyrmion gas. You have all these antiskyrmions forming, but instead of arranging themselves in a neat, ordered pattern, they're jumbled up like a swirling mass of tiny magnetic tornadoes.
Okay, I can picture that. Sounds like my last trip to the mall during the holidays, actually.
But why does this antiskyrmion gas even matter?
Yeah, why?
It matters because this unexpected behavior could have a big impact on how these materials might actually function in a real-world device.
Okay.
Think about it. If you're trying to build a super-fast hard drive using antiskyrmions to store data, you need to know if those antiskyrmions are going to stay put or drift around like in this gas state. Understanding these different phases and how they're influenced by things like temperature and magnetic fields is crucial.
So this shortcut, this AI-powered approach, it's not just about speed, is it? It's actually revealing new insights and even new questions that might not have been obvious before.
This shortcut idea you mentioned is key. It's not just about speed, it's about changing the game entirely. This research offers a glimpse into a future where AI isn't just helping us analyze data, it's actively accelerating scientific discovery. Imagine applying this to other complex problems like predicting earthquakes or designing new life-saving drugs.
The possibilities are mind-boggling. We started with the problem of data storage, and now we're talking about revolutionizing entire fields of science. This is why I love these deep dives.
And what's most exciting is that we're just scratching the surface. If we can predict the behavior of these magnetic systems with this level of accuracy, what other hidden patterns and connections are waiting to be discovered in other areas of science? It really makes you wonder what we're capable of achieving when we combine human ingenuity with the power of AI.
It's like we're standing on the brink of a whole new era of scientific exploration. And to think, it all starts with these tiny, swirling magnets. That's it for our deep dive into the world of anti-skyrmions and AI-powered simulations. If this mind-bending journey left you wanting more, don't forget to subscribe and leave us a review. And be sure to let us know what other fascinating topics you'd like us to tackle in future episodes. Until next time, keep exploring.